Are two events independent? Okay. We got kids taking a driver's test. We got male and female, and we have whether they passed or not. The males, they just keep asking, can I go fast? Can I go fast? No, not yet. Can I go fast now? And so they don't do so well in their driver's test first time through. But we have two variables, gender and the test result. So we want to know if these two variables are independent, or these two events are independent, I should say. So here's what we do. We go to the marginal distribution, and we see that there were 50 females and 50 males. There were 70 people that passed the test, and there were 30 people that failed the test. There were 100 people altogether. So here's what we're going to do. We're going to say, let's go find the probability that a female passes the test. Well, we can see that it's 40 out of 100. So the probability that we have a female and that female passes the test is equal to 40 out of 100, which is 0.4. Now, if these two events, being a female and passing the test, are independent of each other, then we should get that same probability just by multiplying our probability of getting a female in this data times the probability that someone passed the test. We want to see if this will also give us the 0.4. Well, the probability of having a female is 50 out of 100, so this is 0.5 times the probability of someone passing the test was 70 out of 100, which is 0.7. When we multiply these guys together, then we find that we only get 0.35. That tells us that the two events, gender and the test result, are not independent of each other. And then that should make sense, because it should depend on your gender as to whether you pass the test or not. We can see, and this is the second way to do the test, what's the probability that you pass the test given that you're a female? Well, if you know that you're a female, then that shrinks the sample space down to those 50 people. That was 40 out of 50 people, 40 out of 50 females that passed the test. That's 0.8. But if we look at the probability that someone passed the test, given that they're male, now out of the 50 males that passed the test, out of the 50 males that took the test, only 30 passed. So this probability is 30 out of 50. Well, that's 0.6. So it depends on gender as to the likelihood of whether or not a person passed the test. So gender is not independent of passing the test or not. Gender is very much dependent. There's a dependent relationship here. And the two ways to test, and we'll talk about this in a sec some more, is you can either multiply the two probabilities together to see if that's what you get in the intersection, or you can look at the conditional probabilities of passing the test, given that it's a female or given that it's a male, and if those differ, then it really does depend on your gender as to whether you're going to pass the test. Now we can take this information and also show it as a Venn diagram. So we could say, okay, let's look at the universe here. Let's look at these two sets. We'll say that this set is whether someone passed the test or not. This set is whether we have a female or not. So if we look at the Venn diagram and we look at the two-way table, we remember that 40% of our people taking the test were females that passed it, so that 0.4 goes there. Only 10 out of 100 people were females who didn't pass it, so this would be 0.1. This is 0.3, and this is 0.2. These are the males who failed the test. 20 out of 100 males failed the test. So we can use this Venn diagram, we can do the same thing. If we came up to the Venn diagram and somebody said, okay, are these two events independent? Well, you look right there at the intersection. You can see that the intersection of selecting a female and that person passing the test is equal to 0.4. If the two events are independent, female and passing the test, then it should be that you will end up with that 0.4 by multiplying the probability that you get a female, which was 0.5, there's 50% are female, times the probability of passing the test. Altogether, 70% of the people passed the test. But when you multiply that together, you get 0.35. So, by multiplying the two probabilities together and not getting what you find in the intersection, again, your conclusion is these are not independent events. It matters. It depends on your gender as to the likelihood of passing the test. And then once again, we can do it this way. We can also say the second test of independence is the probability of passing the test, given that you're a female, still equal to the original probability of passing the test? Well, if we look at the probability of passing the test, we see that altogether there were 70% of the people that passed the test. So this is 0.7. But if we look at the probability of passing the test, given that we have a female, we can shrink the sample space to just the females. So ignore them, but just in the female group, what's the probability they pass the test? 0.4 out of 0.1. So this is 0.4 out of the 0.5 altogether in there. That's 80%. So it's not true that 80% is equal to the 70% that we could get. So since the conditional probability is not still equal to the original probability, then these two events are not independent. So those are the two tests for independence. This is the one we just looked at to say that the conditional probability has to still be equal to the original probability that event A occurs, or double check to see that what's in the intersection in regards to probability is what you get when you multiply the two events' individual probabilities together. We'll finish it up with Venn pizza. Somebody years ago showed me this at a conference and I thought it was absolutely excellent. We look at this pizza. Let's suppose we're going to some place that doesn't give you a whole lot of toppings and charges you not much money. Little Caesars, perhaps. Anyway, so Little Caesars pizza, you ordered pepperoni and sausage pizza. You only paid $5 for the thing, so it's not like you're expecting pepperoni on those two pieces. There's only 6 pieces of pepperoni and 4 pieces of sausage. And you look at that thing, and before you take it home with you, you say, you know, I wonder if the two events, getting a piece with pepperoni and getting a piece with sausage, are independent of one another. Well, let's take a look. Let's investigate. We want to know, well, here's the deal. Our first test is, it should be true that the probability of getting a piece with pepperoni and sausage is equal to what you get when you multiply the probability that any one piece has a piece of sausage or pepperoni on it times the probability that any one piece has a piece of sausage. First, let's go find this. Looking at the Venn pizza, what's the probability that any piece has both pepperoni and sausage, the intersection there? So we see that 1, 2, 3, 4 out of the 8 pieces have both pepperoni and sausage. So we're going to put a little question mark here. We want to know if this is equal to this. And if we simplify this up, we can see that that's a probability of 1/2. So the intersection has a probability of 1/2. If these are independent events, then this should be true. Well, we multiply the probability of getting pepperoni. There's 1, 2, 3, 4, 5, 6 pieces with pepperoni out of 8. We're going to multiply that by the probability of getting sausage. There's 1, 2, 3, 4 pieces out of 8 that have sausage. Let's just go ahead and write that as 1/2 to make it easier for ourselves. When we take 6/8 times 1/2, we end up with 3/8. So we ask ourselves the question, today, is 1/2 equal to 3/8? No, it is not. So because the probability of getting a piece with both pepperoni and sausage on it is not the probability you would get if you just multiplied these probabilities together, then they're not independent. Okay? So what we can do is we could say, you know what? If we took this one piece of sausage and we put it up here, now are the events independent? Well, let's see. Would you now get that well, let's take a look. Look at the Venn diagram. What's the probability of getting a piece with both pepperoni and sausage on it now? Well, now there's only 3 pieces out of the 8 that have that, so that would be 3/8. Oh, is that indeed equal to the 2 probabilities multiplied together? Bet your sweet Bippy. So now we have made the 2 events, getting pepperoni and getting sausage, independent. The second way, the second test that we can run to analyze this is to ask ourselves, okay, let's focus on pepperoni. What's the probability of getting a piece of pepperoni given that the piece has sausage on it? Is it still equal to the original probability that a piece had pepperoni on it? Well, let's look again at the original probability that a piece had pepperoni on it. There were 6 pieces out of 8 that had pepperoni on it, so 6/8 is 3/4. So the probability that a piece of pizza that has pepperoni on it was 3 out of 4, 3/4. If the two events are independent now, then it should be true that this conditional probability, the probability that a piece has pepperoni, knowing that the piece has sausage on it, this probability should also be 3/4. Well, let's see if it is. So we look up here and we say, okay, we were given that the piece has sausage on it, so that would be this piece, this piece, this piece, and this piece. Don't know how to use red when red is the do. Okay, out of those 4 pieces, how many of them have pepperoni? By golly, 3 out of the 4. So this conditional probability is 3/4. Aha, there we go. The conditional probability is equivalent to the original probability, so these are independent of each other. However, once again, if we put this piece down here, remember that was when there was no independence? Well, now what would happen? The original probability of getting pepperoni is 3/4, but now the probability of getting pepperoni on the pizza, given that the piece had sausage, all 4 pieces with sausage would also have pepperoni. So the probability of getting pepperoni on a piece, knowing that the piece already had sausage, would be 4 to 4, not equal to the original probability. So again, those would not be independent of each other. Independence is an extremely important idea in probability and statistics. It crops up in a bunch of different contexts and ways, but it's really, really important for us to understand, in this case, whether 2 events are independent. Later, we're going to look at random variables as to whether they are independent.